Okay, so first of all, announcements. I have asked you to verify if your WebAssign login is working by yesterday. So hopefully you have all done that. Again, it's not that I won't help you troubleshoot after yesterday, but at this point, I'm going to assign homework number 1 very shortly. Actually, I think I actually already did. I did this morning. So homework number 1 is available. If you could come around the side when you come in, and I'm worried about the camera, and also you walked right across it. So try your WebAssign login. I'm happy to help you, but homework 1 is already available. It is due not this weekend, but next weekend. And so I don't want to hear any of this, my WebAssign isn't working the day before. I'm not going to scramble and drop everything I'm doing to fix it right away. So, and the homework 1 deadline is firm. Okay. Other than that, you do have your first lab experiment this week. That is the intro skills. Depending on when you have your lab, it will be starting tomorrow or later. As a reminder, pick up the lab manual from the bookstore and read the error analysis and Excel tutorial section in there in preparation. So that's what we have coming up. Are there any questions before we get started? Yeah?
I just want to make sure we don't have to do the exercise thing on WebAssign, right?
You mean the intro to WebAssign? Yes, it clearly is marked as not for credit. Yeah. So it's up to you whether or not you do some of it or all of it. Stop. Don't. Can you go around the side when you come in? Okay. So what was I saying again? What were you asking about? Yes. So you don't have. You can do some of it. You can do all of it. The idea is it's a sandbox where you can try out the features of WebAssign. Use it there as a resource. But if you email me and you say, I messed up homework 1. I didn't know how to use WebAssign. I'm going to say, tough luck. You know, you should have worked it out.
General question about the triangle one. What thing was the last question?
Okay. Well, I can't do that kind of stuff in class. So if you have questions on that, come see me outside of class or email me. Okay. Okay. So what we're going to talk about to start today is a little bit more introductory material. We talked all about units last time. We have one more skill, one really important skill before we actually launch in what I would formally start to call the physics. So this is called proportionalities. This is a skill that if you work in any kind of field that has equations, okay? So anything in your career that involves equations, this is a skill that is hugely important. In fact, you will find many people that don't know it, and when you use it, they think you're doing magic, okay? So let me explain to you what this skill is all about. This is a way of looking at equations and realizing that if you wiggle one piece over here, this other piece waggles like this without worrying about any of the other pieces. Let me show you first how it works on a very simple equation. In fact, the simplest equation. Y equals x. That's an equation which means there are two things, one called x, one called y, and they are the same thing. So for instance, if x is equal to 1, well, then y is equal to 1. If x were, say, I don't know, 3, then y is also 3. Now, I want to point out something that's perhaps obvious, that if I take the value of x and I make it go from 1 to 3, I've tripled it. So I'll mark that as times 3. Well then, obviously the value of y will also triple because, of course, if x and y are one and the same thing, of course whatever you do to x happens to y too. But let's check out, maybe x and y are not equal. How does this work still? So let me take another equation, which I'll say y equals 5x. So then, y and x are not equal, y is always 5 times bigger. So for instance, if x is equal to 1, then y is equal to 5. And let's try the same kind of thing. Let's try to make x, instead of 1, let's make it 3. So I've tripled it from its previous value. So x has gone from 1 to 3, so that's triple the value it was previously. Well, if x is 3, what's y now? 15. And I want to point out that y has gone from 5 to 15, so that's also tripled. And so the point I want to make is that these two equations share something in common. And what that something is in common is that whatever you do to x, the exact same thing happens to y. If you triple x, y will triple. If you quadruple x, y will quadruple. If you have x, y will have. They have the same relationship in this equation. And what we try to do is we try to figure out a way to notate the fact that y and x have the same relationship in both of these equations, even though one has a 5 in the front and one doesn't. Here's our notation. Y is proportional to x. So there's a symbol there called the proportional symbol. It's not the same as equals. And in fact, we are using it to talk about two different equations which are not even the same. What we are simply saying is that y has a certain relationship to x. Okay? And we say that this is y is directly proportional, or sometimes we call it linearly proportional. And so what a direct or linear proportion is that whatever you do to x, y will have the same thing happen to it. Okay? So examples would be, I already mentioned that if you triple x, y will triple. If you wiggle x in a certain way, y will wiggle in the same way. You can use this for any number, and if you don't believe me, try it out and convince yourself. You could do it with a half. If you have x, then y will have. In fact, I can just have, instead of 3 or a half as specific numbers, let me use a smiley face. So whatever factor you affect x by, y will be affected by that same factor. That is the essence of what's called a direct proportionality. Yeah?
Is there a limit on the pattern of the relationship between y to x? Because if y equals to 5 and plus 3, then
Right, so this is only going to be true for multiplication and division. If there are some added, something that's added or subtracted or something like that, this is not going to hold anymore. Okay, that's a good point. But many equations, of course, are only combinations of multiplication and division, and this is a very useful tool. So this right here is the essence of a direct proportionality. It's a different way to say that y is proportional to x. Let me just give you a taste of when this would be useful. Let's say instead of knowing the number 5, let's say it's some unknown number, which I'll call a, right? It's some other variable. So a is a constant, but you don't know what its value is. And so in that case, you might think that you would be stuck, because if you don't know the number, how are you going to do anything with this? And yet, even though you have no idea what that constant is, you know that if you do something to x, that same thing will happen to it. So that's why people that don't know this skill start to think it's magic. It's like, how did you do that? You don't know the value of a. You don't need to know the value of a. You just need to know that x and y have a certain relationship within a bigger equation, even if there are other elements of that equation that you don't necessarily know. Okay? So we can conclude that as long as we know a is a constant, it's not a changing value. That's another example of a linear proportionality. Now, there are other proportionalities. They're not all direct or linear proportions. And so let me take a look at another example of something that is not quite that. So let's take a look at the equation y equals 5x squared. And let's first take it out for a spin with some numbers, and then we can get a little more abstract and use proportionalities. So for instance, if we put in x equals 1, what is the value of y? 5. 5 times 1 squared is 5. Let's now take the value of x and, I don't know, let's double it. So we're going to double the value of x times 2. If I do that, what's the value of y? 20. That is not a doubling, right? The value of y has gone from 5 to 20. That, in fact, is a factor of 4. If you take 5 and multiply it by 4, you'll get 20. Where does the 4 come from? Well, the 4 is, of course, 2 squared. And the reason why that happened is because when you do something to the value of x, x is, of course, inside a square. And so whatever you do to x is going to get exaggerated by the fact that x is squared. Okay? In fact, in this equation, we say that y is proportional to x squared. So this is another form of a proportionality. It's no longer a linear or direct proportionality. It's a different relationship that y and x have to each other in this equation. If you were to sum up this relationship, we saw that if x is doubled, then we see that y is actually quadrupled. Or if we want to do it not just in terms of a specific number, let's do it in terms of smiley faces. If x goes to smiley face times x, then y goes to smiley face squared times y. Okay? So that's just another way to encapsulate the idea that these two have this relationship in the equation. And that relationship will hold even if the number in the equation in front, it doesn't have to be 5. It could be any number. It could even be 1. But that's not going to change the fact that y and x have this relationship in this equation. If you want, I can show you even a different way to work this out. Let's start with the equation like this. And then what I'm going to do is I'm going to say the new value of x is going to be, like I said, 2 times the old value. So that means the new value for y is going to be 5 times the new value for x squared. And then I'm going to go ahead and put in here 5, and then, of course, if the previous value of x times 2 is the new value, then I'm going to sub that in like this, and then I'll distribute. That's 5 times 2 squared times x squared, right? You can distribute the power. And then you can pull out the 2 squared, which is a 4, and then the rest of it, what's the stuff in parentheses? That was the old y. So this is 4 times the old value. So we've discovered that the new value of y is 4 times the previous, which is, of course, what we already said. This is just an alternative way of seeing it. So you can kind of see how it works out that whatever you do to x gets exaggerated, right? Because whatever you're doing to x is inside the square, and it's going to get exaggerated by the square. That the square distributed across not only the x, but also the 2, which is how we affected the old x value. So This is a skill that not only will you have at least one problem on your homework 1 dedicated to it, but you will use it throughout. You will use it throughout the semester, and if you really get the hang of it, you'll find yourself using it in any type of equation where you have a bunch of variables that are multiplied or divided. Let me jump straight to an example which has a lot of stuff going on, and we can kind of make sure that we're all solidified on this. Before I go to this final example, are there any questions on what I've talked about so far? Yeah?
So, y being proportional to x squared, what would you call that instead of being directly proportional?
At some point, you just start saying, like, y is proportional to x squared without giving it a special name. Direct or linear is just such a common one that it kind of gets a name. But like, if let's say you had y is proportional to x to the 1/7 power, there's no special name for that. You just say y is proportional to x to the 1/7. Yeah. The direct or linear proportion is reserved for just that simple one that we talked about first. I guess you could say this is like a parabolic or quadratic proportion, I guess, but that requires you to know that when things are squared, they're sometimes called parabolas or quadratic. It's not important to me what it's called, right? It's important that you understand what's going on. Are there any other questions? Okay, so let me show you something that is kind of like a culmination of these ideas. Let's say you have some equation that looks fairly complicated. Let's call it, I don't know, let's call it xz squared over the square root of q. Okay? This isn't an equation from physics. I just made this up. The point is not really important what the equation is as long as you look at it and you understand the relationships. So I'm looking at the, and let's throw in a factor in the front. Let's make it, I don't know, 7. Let's throw in a 7 in there. Okay? So here's what I look at this. This equation has a lot of variables. But one thing I notice immediately is that y is directly proportional to x. So if you assume nothing else, you're not looking at anything else, assuming everything else is constant, if you doubled the value of x, then the value of y would double. Okay? You can see that y is proportional to z squared. So whatever you do to z will get exaggerated in its effect on y. And finally, you can see that y is proportional to 1 over the square root of q. So, y has a certain relationship with each of these variables. Okay? And so here, now that I have taken the equation apart like that, I can start saying, let me wiggle this and wiggle this and wiggle this and see how it all affects y. So let's say, for instance, I'm going to double the value of x. I'm going to triple the value of z. And let me quadruple the value of q. Now keep in mind that I may have no idea what the original values are, but someone's just telling me whatever they are, this is what I'm going to do to them. This is how I'm going to change them. And what I want to find out is what is going to be the effect on variable y. So I'll show you 2 different ways to do this, and whichever one makes more sense to you is more your favorite, you can go with that. They're basically equivalent, and if you understand them both truly, you realize it's the same thing, but maybe one will kind of grab you a little bit more intuitively at first. So you can do it in pieces. So in pieces, if you double the value of x, and x is directly proportional with y, what are you going to do to y? It's going to be doubled, right? Okay, so that is the effect that your wiggling of x will have on y. If you triple the value of z, and y is proportional to the z squared, how are you going to affect y with that? 9 times, that's right. So y is going to be 9 times its previous value because of that factor. Now this is the trickiest one, okay? So maybe you can do this in your head right now, maybe not. If you quadruple the value of q, what are you going to do to y? You're going to have it, that's right. Because the 4 is going to be down below, because that's where q is, and it's going to get square rooted too. So because of that factor, you're going to have y. And so those are the different things that will happen to y, and so what we do is we just accumulate them. Overall, the y value, we said it should double, it should be multiplied by 9, and it should be halved, and that should be the overall effect. So the 2's actually cancel. So overall, you will take your previous value and make it 9 times. Now let me point out how useful this is, okay? Let me point out that maybe you don't know the values of x or z or q to start with, but you do know the value of y to start with. Right? Someone has told you that the result of this equation doesn't tell you what the numbers are, but the result here is something. If then you get told that these values which you don't know in the first place are manipulated in known ways, you can say that whatever the old value is, the new value is 9 times the previous amount. So people start to think you're doing magic because it looks like you're working with incomplete information. But that's the beauty of proportions, is that you can wiggle some little piece over here and understand its effect over here without necessarily worrying about the rest of it. Okay? Now I said I'd show you 2 different ways to do this, so let me show you the kind of more formal mathematical way to do it. Maybe you'll like this better. Maybe you won't, in which case if you understand this method that I just did, you're fine. So I'm going to say that I'm interested in the new value of y, and that's 7 times x new times z new squared over the new q value. So that's by definition, the new value of y is when I have updated all the values of my individual variables. So then what I go ahead and do is I plug in what all of those new variables are in terms of their old ones. So I plug in 7, that's a part of the equation. I plug in that this is 2 times the old x value, so 2x. Z is 3 times, so that's 3z. So and that's squared, don't forget the square. And then I divide by q new is, we said, was 4 times the previous one. Now, while that looks like a big mess, what I'm now going to pull out to the right is all the stuff that used to be y in the first place. So the new factors are a 2, a 3 which gets squared, and a square root of 4. And then everything else, 7x z squared over square root of q. What is that quantity in parentheses? That was the old y value, right? So this right here was the old y value. So our new y value is all these factors here, 2 times 3 squared over square root of 4 times the old y value. Well, this, of course, 2 times 9 over 2 is this stuff right here, right? So there you have it. The answer will be the same, right? 2 times 3 squared is 9, divided by square root of 4 is 2. So it's the same thing that I got previously. So there's a little taste of how to do proportionalities. And again, if you really get the hang of it, this is something you will use even if you never use physics again, if you ever just use an equation again. Are there any questions on that before I move forward? Okay, so let's start to slowly move into physics. So the first thing I need to do in physics is to talk to you about, there's two different kinds of quantities. Find a decent pen that's not running out. So scalars versus vectors. These are the two different kinds of quantities we'll be working with in this class. Scalars are the kind of things that you've used since you've ever worked with numbers back in elementary school. You didn't call them scalars because there was nothing to confuse them with. Okay? These are quantities which have a size only. Some quantities just lend themselves to just saying how much. Here's an example. 70 kilograms. Okay? That's about my, that's a reasonable mass for a person. Okay? 70 kilograms. You can say, I'm 70 kilograms. It's just an amount. Of course, it has units, but it's just here's how much, and that's kind of the end of the story. A vector is a quantity which naturally has two pieces of information bundled with it. A vector has a size and it has a direction. Some pieces of information, it just makes more sense to do it this way, right? If someone walked up to you in the cafeteria and said, hey, can you tell me where the library is? If you told them 100 feet, they'd be pissed. What do you mean? Which way? Naturally, 100 feet that way, right? So you're saying how much and what direction, okay? So an example, 100 feet to your left, okay? So there you're naturally bundling two pieces of information together, and whether or not you called it that, you are giving someone a vector. Some pieces of information just naturally lend themselves to that. It would be very strange to say I'm 70 kilograms to the left. That doesn't make any sense because mass is not a vector. But some quantities, it makes sense. So what we will do in this first bunch of stuff that we do is we will introduce a bunch of quantities that are useful for physics, some of which are scalars and some of which are vectors. One of the ways that we notate whether something is a scalar or a vector is we often give a special little hat. So if a quantity, let's say q, was a scalar, we just say q. But if that was a vector, we'd say q, and then we'd put a little cute hat on it. Okay? And that hat just indicates, you don't literally vary the direction of the hat, okay? But the hat just indicates that there's a vector quantity. So you can just look at that and know that. Now, as far as how we notate direction, we're going to zoom down and simplify our lives greatly just to start with and kind of learn this stuff in baby steps. So we, of course, live in an environment which has three spatial dimensions, right? You can go this way or this way, this way or this way, this way or this way, right? You can go left, right, up, down, front, back, right? So let's zoom down and assume a hypothetical one-dimensional universe. Your options to move are greatly limited. You're basically restricted to moving along a line. So let's call it an x-axis. Let's set an origin, or a reference point called x equals 0. And you can be anywhere you want along this line. You can even be along the negative x-axis. But that's your whole universe there. Okay? And so direction is greatly restricted. You can either move to the right or you can move to the left. And that's kind of it. You can't do anything else. So notice how we have taken something which can be very, very seemingly complicated in 3 dimensions, right? If you're trying to tell someone where to go, you often have to point, right? right? Because there's an infinity of different directions you can have, right? You can point this way or this way or this way or this way or this way, right? There's an infinity of them, because no matter how close two directions are to each other, if they're not exactly the same, you can always squeeze one in between, right? So what we're doing is we're saying, let's not worry about that right now. Let's not jump in the deep end. Let's just go onto a line where you have two choices. You can move one way or the other way, and that's it. Now, how could we notate that? Well, we have two mathematical signs, plus and minus. Make a nice pairing. So let's say that when you move in the direction that's the same as the positive x-axis points, we call that the positive direction. And if you move the opposite way, we call that negative. And by the way, that is true. It doesn't matter where you are. It's about the direction that the arrow points. So if you were over here or over here, it doesn't matter. As long as you're pointing in the same direction as the positive x-axis points, that's positive. And if, no matter where you are, if something points in the negative x direction, we call that negative. Okay, so it's just a matter of one way or the other way. Think of it as an arrow, and you're just looking to see where the arrowhead points. Okay? So that's going to be in one dimension only. Plus and minus can describe direction completely. So, with that in mind, I'm going to give you a little preview of all the different quantities that we're going to introduce, a whole mix of scalars and vectors. I'm going to get them out on the page just so you have them for reference, and then I'll go through them carefully one by one. Okay? So these are what are going to be called the kinematics variables. The word kinematics is just a word which sounds fancy for describing motion. Okay? Kinematics is basically description of motion. Description of motion. It's the same root word as kinesiology. Maybe some of you are kinesiology majors, which is the study of motion. That's usually what you study as an undergrad if you want to go to physical therapy school. Okay? So our first order of business in this class is to learn to become expert at describing motion. The why will be left off till the following unit. We'll peel one layer of the onion away, and then we'll ask, why do things move the way they move? But before we do that, we need to become expert at describing motion. If we see a motion, if we have the language to describe what's going on. So here are going to be the things that we talk about. We're going to talk about the position vector. And notice it has a vector hat, so it tells us right away it's a vector. You don't have to write down that it's position, because I'm going to go through every one of them individually, and then I'll write it down as I go. Then the displacement vector. Then distance. Distance doesn't have a vector hat. That's a scalar. That's how you know. You look at the top, see if it has a little hat. These are all measured in units of meters in SI. They all have the same units, but they all talk about different things. So just because they have the same units doesn't mean they don't have their own differences. So we'll talk about those. Then we'll talk about average speed and average velocity. Notice one of those has a vector hat and one of them doesn't. Then we'll talk about instantaneous speed and instantaneous velocity. And these are all in SI units going to be measured in meters per second. That right there, when we finish discussing that set of stuff, that will be the end of your homework 1. So I'll talk about those. I'll probably talk a good bit about them today, and I'll probably finish talking about those quantities on Friday. So that puts all the material for homework 1 in your hands about a week before it's due. Okay? That'll be the end of homework 1, but it's not going to be the end of the kinematics. We still have a little bit more to discuss. We'll talk about something called acceleration, and the units of that are going to be in meters per second squared. I should mention that there is such a thing as average acceleration and instantaneous acceleration, although we will blur the line between them in this class just to keep things simple. And then, finally, the one thing we do need to have for motion is, of course, time. We need to keep track of it in time. So at first, we'll call it delta t, and then later, just to keep it more short, we'll switch to t. So that's delta t, or later on t. And of course, the units for that are going to be in seconds. These right here form the things that we will look at in our study of motion. And we'll flip these every which way. What we'll do is we'll introduce them one by one, and then we'll start cracking away at their interrelationships. And then we'll take our study and we'll expand it away from one dimension into 2 dimensions and higher. And we'll find that our time learning all this stuff in a simplified one-dimensional universe where the only motion possible is along a line is not time wasted. In fact, the skills we learn there, with a little bit of trickery, can be applied to 2 and 3 dimensions of space. So our focus is going to be on one-dimensional kinematics at first, then 2-dimensional and higher kinematics, and by the time we get around to something besides kinematics, that'll actually be homework 4. Okay? So homework 4 is when we crack the next layer of the onion and ask why. Okay? Not just that things move in a certain way and how do we describe how they move, but why they move that way. So that's giving you a little bit of a preview of what's coming. So the end of homework 1. Homework 1 is basically the kind of intro skills and a little bit of kinematics. Homework 2 is all about one-dimensional kinematics. Homework 3 is all about multi-dimensional kinematics. That's kind of where we're going with this. Okay. Are there any questions before I rewind and start introducing these one by one? Okay, so let's go ahead and start talking about these guys. I guess I'll erase the rest of them and focus in on these first 3. I think I have a shot at talking about these 3, at least getting to mention all 3 of these by the end of the day. Let's talk about the position vector. This is a way of indexing where you are with an arrow. So it's a way of indexing an object's location relative to an origin which is x equals 0 with an arrow. And again, for those of you that might not be used to the term origin, I know it's a very suggestive term. It sounds like where the object originates. Okay, that's not what it means. The origin is x equals 0. It's a reference point. You don't have to have the object start there or finish there or ever go there, but it's someplace where you're referencing the motion. Okay? So for instance, on a football field, you have the 0-yard line, but a given play does not have to start always at the 0-yard line, right? It's just a reference. Here's how it works. The tail of the arrow is at the origin, and the head is at the actual location of the object. That gives you a recipe on how to form the position vector. Okay? So just to make this a little more tangible, actually I'm going to have to erase this just because I need a little more board space. So let me go ahead and draw a number line. And let me draw an object, let's say a person. And let me suppose, for instance, I somehow know that that person happens to be standing 3 meters to the right of x equals 0. There's some reason why that x equals 0 is being referenced there. And we know that the person is actually just standing there 3 meters to the right of it. So let's follow the recipe. The tail of this arrow should be at the origin, and the head should be where the object is actually located. So we follow the prescription like this. There is our position vector, x vector. So let's write down what this position vector is. Now, first of all, with any vector, there's two pieces of information. One is the length of it. So how long is this arrow? 3 meters. But that's not the only piece of information. The other one is which way it points. So does it point in the positive direction or the negative direction? Positive. So that position vector is plus 3 meters. So there's the two elements of the vector. There's the size, and there's the direction. It's very simple to notate vectors in one dimension. All you have to do is put in the size and then put in a plus or minus in the front as appropriate. Now this is where someone usually asks me, how does WebAssign even know that you're putting the positive there? If you leave it off entirely, doesn't it assume it's positive? Yes. Yes, it does. So if WebAssign asks you for a vector in this form, can you get away with leaving the plus explicitly off the front? Yes, you can. It'll let you slide. But I'll tell you this, if you're not used to thinking about the plus being there when it should be there, then you're going to forget the minus when it should be there, and then WebAssign will ding you. Okay? So if something points in the negative direction, according to the axis choice, you need to put the negative there. Okay? So get used to thinking about vectors as always having an associated direction. And by the way, that is one thing that, as much as it might seem like it's a minor mistake, I can't give points back for that on the homework. Okay? If it's a rounding issue, I really don't care. Okay? I'm not a stickler about significant figures. I give you some rules of thumb on the WebAssign guide simply to save you the aggravation of rounding off too much and WebAssign just thinks you did it wrong. Okay? So I'd say err on the side of 3 significant figures. But the system is never going to penalize you for too many, and I don't really care either. Okay? So anytime you can get points back for round off, that's fine. But signs matter in physics. They matter a lot. They indicate something. So I can't give points back for errors in physics. Okay? So that's the position vector right at the moment with this person just standing there. It's a way of referencing where they're standing relative to some reference point. Are there any questions on that before I move forward? Okay, I'm going to move forward by letting the person move forward. So in physics, we usually like to let people do things and not just stand there. So let's let this person go over here. So they're going to take a walk, and they're going to go somewhere else. And let's say, for instance, I happen to know that this was a 2-meter walk further to the right. And so now their position vector is no longer the same thing. It's changed, right? So let me follow the prescription for drawing it. Its tail should always be at the origin, x equals 0. And its head should be at the location of the person. So there is the position vector now. How long is that arrow? 5 meters. That's right. And is that point in the plus or minus direction? Plus. So the position vector now is plus 5 meters. Again, there's the size of it, and there's the direction. So the common theme you should notice is that a position vector, its tail is always rooted in the same point. It's always rooted at x equals 0. If you happen to be standing to the right of x equals 0, you will have a rightward position vector. If you happen to be standing to the left of x equals 0, you'll have a negative position vector, right? The tail is always tied down. It's the head that moves to accommodate where the person or whatever is actually located, okay? And one of the things we might want to do is specify which one came first. So we might want to say this is the initial position vector. So I'm adding a subscript x initial, and then I'm going to call this x final. That's the final position vector. That indicates which one came first and which one came later. Question?
If there's more than 3, is there like a middle term?
Usually any motion has a beginning and an end. And if we were wanting to refer to a position in the middle, we would just say it's the position at like t equals whatever, right? So initial and final are kind of reserved for the very beginning and the end. And of course, what we mean by beginning and end are the beginning is what we care about, and the end is the final of what we stop caring, right? And we can also refer to the position vector anywhere in between, but we'd probably just call it, this is the position at some intermediate time. Any other questions? Okay, so let's add to this another very related quantity called the displacement vector. Displacement. Displacement is basically, you can see it's another vector. It's got a vector hat, and the purpose of it is to describe the net effect of a trip of some kind. It's basically, if you know the English word for displacement, it's how much you are displaced from where you started. So it talks about what is the overall effect of a trip. The prescription for drawing it is at the tail is at the initial location of an object, and its head is at the final location of an object. So it's just a little bit of a different recipe for how to go about drawing this vector. Instead of its tail always being tied down to some arbitrary reference, it is marked, the beginning and the end of the arrow is marked by the motion. So the reason why I introduced this next is that this is a handy diagram where I can also add that new vector. So this is the prescription for drawing it. That displacement arrow looks like this. I draw an arrow that connects the initial and final locations of that motion. And we can go ahead and write down that that displacement, first of all, is that a positive or negative pointing arrow? Positive. It points to the right. And how long is it? 2 meters. So that would be the displacement of this trip. If you are wondering if there is a recipe for finding the displacement from the position vectors, there certainly is. If you want to relate them, you go like this. This is one method of finding the displacement vector. If you have the position vectors already lying around, you subtract them in that order. You put in the position vectors, and you put them in, signs and all, plus or minus, whatever they are. You subtract them in that order, and this will actually give you the displacement vector with the correct sign. So it all works itself out, and I'll leave it to you to convince yourself that that is the case. There is also a second method of getting displacement, which I will say, I'll call it this. Just write it down. I don't know how else to say it. Just write it down. Now, what do I mean by that? If you know that someone had a trip like this, where they walked 2 meters to the right, then you know the displacement. You just write it down. that may be something you can write down even if you have no idea what the position vectors are. And the reason you might not know that is because no one told you where the origin is. You don't know where x equals 0 is. You might know that the plus x direction is to the right, but no one told you x equals 0. Then you can't say what either of the position vectors are, the initial or the final. But if you know that someone walked 2 meters to the right, then the displacement's right then and there. So as much as this seems silly, we will oftentimes just do that. We won't bother to set an origin. We'll just write down the displacement. If you end up 2 meters to the right of where you started, displacement's plus 2 meters. That brings up an important difference between displacement, but displacement is what we call origin independent. You do not need to know where x equals 0 is in order to have the displacement be defined. All you need to know is what's the positive direction and how far in that direction you went. Of course, that is in contrast to the position, which is origin dependent. You can't even write down a vector for position until you know where the tail is supposed to be. Okay? And that difference right there is something important that we'll come back to later in the class. Okay, so that's it for today.